So today we're going to be looking at the past questions on simple harmonic motion, okay, from JAMB, WAEC, okay. Even if you have exams different from these to write, of course, you could have this as an eye-opening experience to, or an insight into what the questions you'll be facing in your exam can be like. Okay, so I would say, as usual, you can join us in solving these questions, but then it will be far better if you can pause the video, solve the questions on your own first, and then come back, or you download the PDF. You download the PDF from the description, then solve them on your own, and then come back to compare what you've done with what we've done. And then probably if there are places you can be corrected, you can take corrections from this video. Okay, so let's move on to solving the first question. So the first question is: the maximum displacement in either side of the equilibrium position of an object in simple harmonic motion represents A, the period, B, amplitude, C, wavelength, D, frequency. Okay, so what this first question is saying is, you might have, let's say for example, a simple pendulum. This is the equilibrium position. Okay, it's saying the maximum displacement on either side of the equilibrium position. This is the equilibrium position. So now that displacement on either side, this side or this side, all right, of an object in simple harmonic motion represents what? So what's that maximum displacement? Okay, so of course that is the amplitude. Okay, that's the amplitude of that motion. All right. Okay, the second question: a loaded spring is set in simple harmonic motion. The force that tends to restore the load to its equilibrium position is dash. Okay, now I've heard a lot of students answer gravitational here. Okay, but let's not get this twisted. This is a very important question, because the question that was asked was a loaded spring. Now, if we're talking about the simple pendulum, okay, the simple pendulum, the restoring force is gravity, because I mean, look at the simple pendulum. There's no force acting on this object to bring it back. If you displace this object to this point, okay, the only thing that brings it back to this equilibrium point, the only thing that restores it, is the force of gravity trying to pull it to the ground. So because of that pull in this direction, it tries to go with force of gravity, but this cord or this string won't let it go. So it just goes in that kind of motion to this point of equilibrium, where it can now stage an opposition to the force of gravity. All right, so this is the equilibrium position. And now in this case, our answer will be gravitational, because that's the force that tends to restore the load. But we're talking of a loaded spring. So let's say we have this. Okay, I want us to picture this properly. So of course this is a cord and this is a spring, and then it's, let's say it's displaced in this direction. Okay, let's say it is displaced in this direction and the spring restores it back. What force do you think did that restoration? Is it the force of gravity? Okay, this is an object on a spring now, all right, and it is displaced in this direction, and then you take your hands off it. Do you think it's the force of gravity that restores it? No, it is the elastic potential of the spring. So there's a difference between the loaded spring and the simple pendulum. For the simple pendulum, it is gravitational. For the loaded spring, okay, it is elastic. All right. Okay, third question says, if a freely suspended object is pulled to one side and released, it oscillates about the point of suspension because the A, acceleration is directly proportional to its displacement. B, motion is directed away from the equilibrium point. C, acceleration is directly proportional to the square of its displacement. Then D, velocity is minimum at the equilibrium point. So the answer to this question is A, acceleration is directly proportional to its displacement. If you even remember, we have a formula that says A equal to minus omega, all right, times x. Okay, you see from this equation that the square is on W, that's omega. X has no square on it, so A is directly proportional to x. All right, so it's directly proportional to its displacement. Okay, so that's the question. That's the answer to number 3. So let's move on to number 4. The length of a simple pendulum is increased by a factor of 4 by what factor is the period increased? Of course, we can see this is a why question. Okay, so the length of a simple pendulum is increased by a factor of 4. By what factor is its period increased? Alright, so we remember the formula we have for finding the period of a simple pendulum, which is t equal to 2 pi root L over G. So what we're going to do here now is that we would have to avoid all the other parts of the equation and then take into cognizance the proportionality between t, the period, and L, the length. Okay, because that's all we need to solve this question. Okay, so we know that t is directly proportional to root L. Okay, all right, so we can take 2 pi and g here to be our constants. Okay, all right, so if 2 pi and g remains constant at all times, then we know that t is directly proportional to root L. Okay, so if that is the case, for us to have our length increased by a factor of 4, okay, of course, for us to have our length increased by a factor of 4, we know that in an equation, whatever you do to the right hand side, you do to the left hand side. So even in a situation where you have proportionality, whatever you do to the right hand side, you do to the left hand side. So since we have introduced 4 to this equation, actually what we introduce is root 4. Okay, because there's a square root sign covering both 4 and L. Okay, so we have root 4L here. Okay, so since that is the case, we have to introduce root 4 to the left hand side. All right, so if we do that, we're going to have root 4t is proportional to root 4L. Okay, which makes sense. Now 4 was not just introduced to L. If 4 was introduced to L, what we'll have is 4 root L. Okay, we are not asked to increase the root of L. We're asked to increase L by 4, by a factor of 4. So that we have done to increase L by a factor of 4, but increasing L by a factor of 4 did not introduce 4 to this proportionality. What it introduced was root 4. All right, because this root sign is binding on the 4. So we have to introduce root 4 to the left. So after we've done that, we're going to be having, of course, this is same as 2t, then proportionality sign with root 4L. All right, which means the period is going to be increased by a factor of 2. All right, so the answer is B. Okay, so that we can easily get from this whole equation. All right, so let's move on to question number 5. The period of a simple pendulum X is 5s. What is the period of a simple pendulum Y, which makes 50 vibrations? In the same time, it takes X to make 20 vibrations. All right, so we have our period to be 5 seconds for the pendulum X. So we're considering both pendulum X and pendulum Y. Understanding that we know that for S, 1 vibration is equal to 5 seconds for X. Okay, so if we're talking about 20 vibrations, how long does it take to make 20 vibrations? Because we need to know that, okay, to know how long this other pendulum Y makes 50 vibrations. Okay, so pendulum X makes 20 vibrations in 100 seconds. Of course, we can get that by multiplying 20 by 5. If 1 vibration is 5 seconds, 20 vibrations is 20 times 5, which is 100 seconds. So this also means that pendulum Y makes 50 vibrations in 100 seconds. Because the question makes us understand that pendulum Y makes 50 vibrations in the same time that it takes X to make 20 vibrations. So pendulum Y makes 50 vibrations in 100 seconds. So we're asked to find the period. Okay, so if 50 vibrations is 100 seconds, then we know 1 vibration is going to be 100 divided by 50 vibrations. And if we do that maths, we're going to have 2 seconds as our answer. Okay, so the answer to this is C, 2 seconds. So question number 6. The period of a simple pendulum of length 80 cm was found to have doubled when the length of the pendulum was increased by X. We're asked to find X. Alright, so we have our length to be 80 centimeter. Okay, so if you remember from the previous question we did where we have t equal to 2 pi root L over G, okay, we brought out the proportionality of t and L and worked with it. We're going to do the same thing here. So we will bring out the proportionality of t and L, but in this case the period doubles. The question says the period of a simple pendulum of length 80 cm was found to have doubled. So this period has doubled. So remember, this whole equation starts with t, okay, with the proportionality sign root L. All right, Okay, remember we have this. Okay, now if this doubles, what happens to this side? If we put 2 on this side of the proportionality, we have to put 2 on this other side of the proportionality. So basically we have 2t, and we have to add 2 to this other side, so we have 2 root L. Okay, but then this is the same as root 4 root L. Okay, because 2 is the same as root 4, so we have 2t proportionality sign root 4L. That's how we got this equation here. Okay, so we are asked to find x, where x is the length of the pendulum, the increase in the length of the pendulum. Okay, so obviously if we have L to be increased by 4, okay, it means 4L will be 4 times 80 centimeter, which would give us 320 centimeters. Okay, all right, so 320 centimeters is the new length of the pendulum, but that's not what we're asked to find. We're asked to calculate x, where x is the increment. Okay, the length of the pendulum was increased by x, so we're not asked to find the final value, we're asked to find that increment. So 320 cm is the final value, so the increment is going to be 320 cm minus 80 cm, which would give us 240 centimeters. So we can see the answer is D for number 6. Okay, so we move on to number 7. Number 7 says a simple pendulum of length 0.4 meters has a period of 2 seconds. What is the period of a similar pendulum of length 0.8 meters at the same place? Okay, so we're going to use the same idea, the same formula. Okay, so T is proportional to root L. All right, the length of the simple pendulum is 0.4 with a period of 2 seconds. They're asking to find the period of a similar pendulum, okay, which has a length of 0.8 meters in the same place. Okay, so if we look at this question very well, we will see that the simple pendulum, the first simple pendulum, has a length of 0.4, but then we're asked to find that of a second one which has 0.8. So you see that the length doubles. We're asked to find the period of a simple pendulum that has doubled in length, okay, or that has double the length of the first one. So of course we can bring in 2L into this equation, or we can bring in 2 into the right side of this equation, and if we do that, obviously we're going to have to add something to this other side, and that will be root 2. Okay, so this will give us T1 equal to 2 seconds. So since T1 is equal to 2 seconds from the question, okay, automatically we have our T2 to be root 2 times 2 seconds, which will be 2 root 2. Okay, so if you check the options for that question, you're going to find 2 root 2 as part of the option, and that's the answer. Okay, but then let's remember that this period was given to us here, okay, as 2 seconds, and so since we have root 2 on this side of the period, the increment for the period is root 2 for doubling the length. Okay, so we just take root 2 multiplied by what we had as t, okay, to give us 2 root 2. So this will be the new period for the pendulum whose length is double of the first pendulum. Okay, so we move to number 8. Calculate the period of vibration of a spring system of force constant 200 Newton per meter when loaded with a mass of 2 kg. Okay, so we know our spring constant is 200 Newton per meter and our mass is 2 kg. So we use the formula T equal to 2 pi root m over k. All right, so if we bring values into the equation, we're going to have, okay, this 2 pi root 2 kg all over 200 Newton per meter. If we simplify this, we're going to have 2 pi times 0.1. Further simplification gives us our answer to be 0.63 seconds. So that's the period of vibration of this spring mass system. Okay, so we'll move on to question number 9. A system performs simple harmonic motion with a period of 10 seconds and amplitude of 2 meters. Calculate its maximum velocity. So of course, we know that maximum velocity is equal to omega A. Okay, omega is same thing as 2 pi f or 2 pi over t times a, where a is amplitude. So if we put in our values, we have 2 pi divided by 10 seconds times 2 meters. Okay, so if we simplify that, we're going to get 1.26 meters per second. So that's our maximum velocity, okay, that we can get from this question. But then I need you to note something. What makes this formula a formula for maximum velocity is A. Okay, this can be x, that's any length of displacement. But once you're talking of amplitude, amplitude is the maximum displacement. So for us to have that maximum displacement, okay, it would make the velocity here the maximum velocity.